this video, we will compare solutions of linear versus nonlinear differential equations. First, we'll talk about existence and uniqueness. So for a first-order linear differential equation put in standard form, that is y prime plus p of t, y equals g of t, we expect existence and uniqueness if the functions p and g are continuous. And there's more, we'll go over this in more detail. Then second, we look at first-order nonlinear functions. So we expect existence and uniqueness of a solution when the functions f and df dy are continuous. There are three other points which we will compare linear versus nonlinear. And the first one is general solution. So if you recall, when we solve first-order linear equations, we often have y equals some function, and then we have a constant c at the end, and then we would solve for c by using different initial conditions. And essentially, once we have this solution y equals something plus c, this expression with the c encapsulates all the different solutions. So there's a general solution that includes a constant, and it includes all solutions of the differential equation. It's all captured here. However, for nonlinear equations, you can have a function y equals some function plus c. So although you have an arbitrary constant, there still may be other solutions that you can't just plug in a different c and get to. So and we will do examples of this, definitely. Then another difference is implicit versus explicit. So for first-order linear equations, we have this solution, this explicit solution that we solved using integrating factors. However, for nonlinear, if you're even able to integrate the nonlinear equation, well, you're in luck. But then once you do integrate, it's quite often that you have to leave it in implicit form rather than explicit. Again, for linear, you always have this explicit form. Then the last thing we're looking at is discontinuity. For a linear equation, all you need to do is look at p of t and g of t. And whenever p and t and g of t are discontinuous, that's where you might have problems in your solution. However, for a nonlinear equation, you actually have to solve the equation to know where you might have problems. So the singularities, the solution of nonlinear equations, can usually only be found by solving the equation and examining the solution. Furthermore, it's likely the singularities will depend also on the initial conditions as well. I usually like to have only one overview slide at the beginning of a video, but I did feel compelled to add this, so I have the existence and uniqueness theorems for both the first order and linear and nonlinear. So that's kind of a repeat, but I also wanted to put two examples here on my overview slide. We will go over the examples in the video. So the first theorem is existence and uniqueness for first-order linear equations. So if the functions p and g, and remember this is the form of our first-order linear equation, so the functions p and g are continuous on an open interval where t goes from a to b, and the open interval contains the point t equals t naught, then there exists a unique function y equals phi of t that satisfies the differential equation for each t in the interval, and that also satisfies the initial condition, y of t naught equals y naught, where y is an arbitrarily prescribed initial value. The proof outline, we're not going to do the proof, but I will say essentially when we looked at how to do solutions for first-order linear differential equations, we showed that this solution here, y is equal to 1 over mu of t, where mu of t is the integrating factor, integral from t naught to t, u of s gs ds, where s is just the variable of integration, plus y naught would be the solution. So the fact that you can find a solution is your proof. Our first example is find an interval ty prime plus 2y equals 4t squared, and y of 1 is equal to 2 has a unique solution. And then do the same for the initial condition y negative 1 is equal to 2. I started by rewriting. I often like to write y as a function of t, just so that I can keep that in mind. So t times y prime of t plus 2y of t is equal to 4t squared. And then I want to get this into this form here, the y prime plus p of t y equals g of t, into this linear form. And I can do that by dividing this equation, the whole equation, by t. And I'm left with y prime of t plus 2 over t, y of t equals 4t, which is linear. You can see it's linear here. In this form, you can see then my p of t is equal to 2 over t, and my g of t is equal to 4t. Both of these equations are continuous everywhere except at t equals 0. And you can see that right here. The p of t will give you trouble for t equals 0. Keeping this in mind, we can now look and find an interval in which this equation with the initial condition y1 equals 2 has unique solution. So if you look at y1 equals 2, it is in the interval t is greater than 0, basically because here t is equal to 1. So we have a unique solution for this interval t between 0 and infinity. For this solution here, for t is equal to negative 1 equals 2, it's in the interval t is less than 0, which means it has a unique solution when t is less than 0, or t is between negative infinity and 0. Now we will consider nonlinear equations. The previous theorem was for linear equations. This theorem is for nonlinear equations. So it's theorem with in bullet point number 2. The existence and uniqueness theorem for first order nonlinear equations. Let the functions f and df dy be continuous in some rectangle, t between a and b and y between c and d. So now the things that need to be continuous are f and the derivative of f with respect to y. Then in some interval, t between t naught minus h and t naught plus h, contained in the interval t between a and b, there is a unique solution, y equals phi of t, of the initial value problem. Y prime is equal to f of t, and y of t naught is equal to y naught. So here, in order to have solutions, you want the function and the partial derivative to be continuous. And I do have a note. If f is continuous, just f, but not necessarily the partial derivative, the existence of the solution is guaranteed, but not necessarily uniqueness. Now we will look at a nonlinear equation and find where it has solution. So we're going to apply the theorem dy dx is equal to 3x squared plus 4x plus 2 over 2y minus 1. And y naught is equal to negative 1. And we'll repeat the same with y naught is equal to 1. First, just looking at this equation, dy dx equals 3x squared plus 4x plus 2 over 2 times y minus 1. So this is nonlinear because the exponent on our y term is equal to negative 1. And maybe you'd think, oh, well, I could just multiply both sides of the equation by 2 times y minus 1, and that would get rid of the next negative exponent. But I still have a problem because here, when I multiply, I'm going to get 2y minus 1 times dy dx. And this is still nonlinear because of the y times dy dx. Remember, if it's linear, the dy dx is just multiplied by a function of t. So like the dy dx still counts as a function of y. So here we have a nonlinear term, which is why we're using this theorem here for nonlinear equations. And according to this theorem, the two things I need to look at are f and the derivative of f with respect to y. So here I have f of y, and I rewrote it, 3x squared plus 4x plus 2 over 2 times y minus 1. And then I took the derivative with respect to x, which is the bottom squared, times the bottom times the derivative of what's on top. And again, we're taking it with respect to y, so this is 0, which is kind of nice. And then I have my top times the derivative of what's on bottom, which is 2. And then it gets simplified to negative 3x squared plus 4x plus 2 times 2 times y minus 1 squared. These are both continuous. F of y and df dy are both continuous except at the line y equals 1, because that's where you get the 0 on bottom. For the initial value problem, y of 0 equals negative 1, you can draw a rectangle around 0, 1. So there's some interval with a unique solution at y0 equals negative 1. When we consider y0 equals equal to 1, something different happens now, because now we're at y equals 1, which is where this function is not continuous. So it lies on the line, and the theorem says nothing now, Because it's not continuous, we cannot apply this theorem. So the theorem says nothing about the existence of a solution. So it's important you realize it doesn't say if df dy is not continuous, it doesn't mean there's no solution, it just means you cannot, the theorem has nothing to say about it. And in fact, we can separate the variables and integrate to get a solution. Now we've taken a quick look at both theorems, the existence and uniqueness of theorems for first-order linear equations, and the things that need to be satisfied is the functions p and g here need to be continuous for there to be a solution. For existence and uniqueness for first-order nonlinear equations, the functions f and df dy need to be continuous, again, nonlinear. For both of these theorems, so this note here, uniqueness implies the graph of two solutions cannot intersect. Otherwise, there'd be two solutions that satisfy the initial conditions corresponding to the point of intersection, and that violates uniqueness. We will do another example. Consider the initial value problem. Y prime is equal to y to the 1/3. Y0 is equal to 0 for t greater than or equal to 0. Apply one of the theorems to this problem and solve. The first thing to note is the y to the 1/3 makes this nonlinear, so we will be applying this theorem here for nonlinear equations and looking at f and df dy. We'll be looking to see if it's continuous. And here is my f of y to the 1/3, which is continuous everywhere, but df dy is equal to 1/3 y to the negative 2/3, so that is not continuous at y equals 0. Our initial value problem is at y equals 0, but since dy dt is not continuous, the conditions of the theorem are not met, so the theorem does not apply. And just a reminder that the theorem, since it's not an if and only if, it's only a if-then, so there might be a unique solution or there may not be a unique solution, but there is this note here. So since f is continuous, according to this note, there is a solution, it just may or may not be unique. The instructions were to solve the equation, so here I rewrote it as dy dt is equal to y to the 1/3, and then I put of t just to remind myself it's a function of t. And this is a separable equation, so I can move my y over and group my y's together and then get my functions of t together. Well, when I divide by y, I get negative y to the 1/3 t dy dt is equal to 1. And then I can integrate both sides with respect to t, and I note that 3/2 y to the 2/3, the derivative of this with respect to t is exactly what's in these brackets because of the chain rule. The chain rule. So, right, if I multiply this, I'd get 1 times y to the minus 1/3, but then I also have to multiply by dy dt, by the chain rule. And on this side, I get t plus a constant c, which means y is equal to 2/3 t plus c raised to the 3/2, and this is my solution. Looking at our initial condition, y naught is equal to 0, so plugging in 0 for t and 0 for y, we have y equals 0 is equal to 2/3, and then we have t is equal to 0 plus c to the 3/2, which implies c is equal to 0, which means our first solution, p1 of t, is equal to 2/3 t to the 3/2. We only briefly mentioned this at the beginning of the video, but for our separable equations, for first-order nonlinear equations that are separable, it may be the case that this, what I call the general solution, and I put it in quotes because if we're not talking about first-order linear equations, it's really not a general solution. In other words, this general solution may not include all solutions. You can't just there are other solutions that are found by not simply plugging in another value of c that you solved for when you did an initial value problem. So in particular, for this problem, there are two other sets of solutions. One is v2 of t is equal to minus 2/3 t to the 3/2. And also if you look, t is equal to 0, so both of these solutions, v of t and this y is equal to 0, will solve the differential equation. We're going to talk more about this, about how there are more solutions than maybe just this that comes out of solving our differential equation when we're looking at nonlinear functions. But for now, we're just going to say we do have a family of solutions that I've written here. Considering the interval of existence, in other words, where do solutions exist? So according to the theorem, the solution of a linear equation with initial conditions exists throughout any interval which the functions p and g are continuous. Again, this is this theorem here. Thus, vertical asymptotes or other discontinuities in the solution can only occur at points in discontinuities of p or g. For example, in the previous example, which I have written below, the solutions are asymptotic at the y-axis corresponding to the discontinuity t equals 0. Remember here we have p of t is equal to 2 over t, so it's continuous everywhere except t equals 0. So around t equals 0, the solutions are asymptotic, but none of the solutions has any other point where it fails to exist and be differentiable, only at t equals 0. And one last point, solutions can sometimes remain continuous even at points of discontinuity of coefficients. That does not violate this theorem. Now we want to look at intervals of existence for nonlinear initial value problems. For a nonlinear initial value problem satisfying the hypothesis of the theorem, in other words, you have f and df dy continuous, the interval in which a solution exists may be difficult to determine. The solution is certain to exist as long as the point t, phi of t remains within a region which the hypothesis of this theorem are satisfied, and this is what determines the value of h in that theorem, this value of h. However, since phi of t is usually not known, it may be impossible to locate this point with respect to this region. In any case, the interval in which a solution exists may have no simple relation to the function f in the differential equation. This is illustrated in the next example. And here are example nonlinear initial value problems, interval of existence. Solve the initial value problem y prime is equal to y squared, y of 0 is equal to 1, and determine the interval in which the solution exists. And here you can see it's nonlinear because of the squared. So here I have y prime is equal to y squared. So my f of ty is equal to y squared. That's continuous everywhere. My df dy is equal to 2y, which is also continuous everywhere. So if I want to solve, now I can separate this equation, gather all my y terms to one side, and I get y to the negative 2 dy dt is equal to 1. Integrate both sides of this equation by dt, and I get negative y to the minus 1 is equal to t plus c. In other words, y is equal to negative 1 over t plus c. Looking at my initial value problem now, plugging in 0 for t, 1 for y, I get 1 is equal to minus 1 over 0 plus c, which is equal to minus 1 over c, implies c is equal to negative 1, and y is equal to 1 over 1 minus t. Now I can look at my interval of existence. Here, if I look at y, obviously it does not include t is equal to 1. So interval of existence is t is not equal to 1, even though my f of t and my df dy shows that it's continuous everywhere. For our interval of existence, then we need to either choose negative infinity to 1 or 1 to infinity. So we need to choose the interval that includes our value of t here in our initial value, which is equal to 0. So in this case, we're going to be looking at the interval from negative infinity to 1. And again, just looking at f of ty and df dy, there was no indication there was going to be a problem. We've alluded to this a couple of times now, that linear equations differ from nonlinear equations in that for linear equations, there's a general solution and implicit solution. Another way in which linear and nonlinear equations differ concern the concept of a general solution. For first-order linear differential equations, it's possible to obtain a solution containing one arbitrary constant from which all possible solutions followed by specifying the values for this constant. For nonlinear equations, this may not be the case. Even though a solution containing an arbitrary constant may be found, there may be other solutions that cannot be obtained by giving values to this constant. For example, this problem here, which we had just done, y prime is equal to y squared, f of t is equal to y squared, and the derivative is equal to 2y, so both of these are continuous. We solved and we got y is equal to minus 1 over t plus c. But when we solve this equation here, you can see that we did divide by 0. Where was that? Because of the negative y squared. So which means y equals 0 was not considered. Essentially, when we move this y squared over and it became y to the negative 2, we were automatically assuming that y would not equal to 0. So when we solved this equation, we had excluded the possibility of y equals 0, when in fact y equals 0 does solve this differential equation here. And this is just one example, but the existence of additional solutions is not uncommon for nonlinear equations. Thus, we use the term general solution only when discussing linear equations. And I have to apologize because sometimes I put general solutions, but I do put it in quotes when I'm talking about nonlinear equations. Another difference between linear and nonlinear differential equations is for implicit solutions, the first order linear differential equation had an explicit formula for the solution. Remember, this was our solution, y is equal to 1 over mu of t being the integrating factor times this integral. As long as the necessary antiderivatives could be found, the values of the solution at any point can be determined. For nonlinear differential equations, usually the best we can hope for is to find an equation capital F of t y equals 0 that satisfies the solution y equals phi of t. Even this can be done only for differential equations of a particular type, of which separable equations are the most important. The equation capital F t y equals 0 is called an integral or first integral or the differential equation, and its graph is an integral curve or perhaps a family of integral curves. F of t y, assuming it can be found, defines the solution implicitly. If the equation is simple enough, it may be possible to solve for y by analytical means and obtain an explicit formula. However, more frequently, this will not be possible, and you'll have to resort to a numerical calculation. So for nonlinear differential equations, most of them you're not going to be solving, and you'll be using a numerical calculation. You won't be able to solve. However, there are certain classes, including the separable equations, which we have looked at and we will look at further, that can be solved. So in this video, just to recap, we looked at the existence and uniqueness of solutions for first-order linear equations and also nonlinear. To have a solution for a linear equation, we put the equation in standard form, y prime plus p of t y equals g of t, and we looked at p of t and g of t. If they were continuous, then we were guaranteed existence and uniqueness of a solution. For nonlinear equations, we looked at the function f and df dy, and if they were continuous, then we were guaranteed existence and uniqueness, and we had these two examples which we worked out in the video. Then we also compared linear equations with nonlinear, first in general solutions versus implicit and explicit solutions, and also discontinuity. So first, for linear equations, general solutions, assuming we had coefficients that were continuous, the coefficients p and g were continuous, there would be a general solution containing an arbitrary constant c. And this general solution would include all solutions of the differential equation. So particular solutions, we could find them by satisfying the initial condition, and then we would solve for the arbitrary constant that would give us a particular solution. But the idea is that we would have a general solution that encompassed all solutions of the differential equation. For nonlinear functions, there's no general solution. So we can find a solution that has an arbitrary constant, but there still may be other solutions that you can't get to just by plugging in a different constant. And we had examples of that, notably when we were separating the equation, if we divided by y, we potentially were dividing by y equals 0, for example, in which case the 0 might end up being a solution. We had just kind of disqualified that while we were solving for it. So there's no general solution here. Then we also talked about implicit versus explicit. So for a linear equation, there's always an explicit solution, which is written right here. For nonlinear equations, often you're going to have to leave things as an implicit solution. So you're going to find y equals phi of t that satisfies the condition of your linear equation, a differential equation, sorry. Phi of t that satisfies your differential equation. And last, we looked at discontinuity. So for linear equations, you can look at P of t and G of t to determine when you will have problems with solutions, whereas the nonlinear equation, you actually often have to, well, first, you may not even be able to solve it, but if you can, then you often have to solve the equation and examine the solution, and also sometimes you have to take into account the initial conditions as well. And that's it for this video. Thank you for watching.